If math has been driving you crazy, or if you're finally admitting you're lazy, and your test grades have been dropping, it's time to get your arrows popping. This is Larry Whittington with Fort Bend Tutoring, and today's tutorial is going to be about graphing cosecant. That's right, one of the 6 trigonometric functions that you can graph in your math class, and you will be asked to graph it. Oh yes, you will. Oh, I'm sorry in advance. And today, guys, we're going to be going over just that, how to graph cosecant. And before we move too far, I'm going to ask for you to subscribe to the YouTube channel Fort Bend Tutoring. That's right, check out all of our free math tutorials. And I also want to give a shout out to all of our current subscribers as well as our donors. That's right, Michael, I'm talking to you. That is correct, sir. Thanks for your generosity. When you subscribe and when you donate, that helps motivate Fort Bend Tutoring to bring you more free math tutorials, guys. So please continue to do so. What I have for you first is a snapshot of the problems that we'll be doing in this video. Check them out. I got 4 functions to graph today. We have f of x equals cosecant x. We have y equals negative cosecant of pi x. We have f of x equals cosecant of the quantity x plus pi over 2 plus 2. We also have our 4th problem, which is y equals 2 cosecant of 1/3 x minus 1. Oh yeah. So fun times are coming. And here we have information about the cosecant function. When you're dealing with the parent function, keep in mind that this is a reciprocal function. It is equivalent to the reciprocal of sine. Yeah, so it'll share quite a few things in common with the function sine. So if you're ever in need of your cosecant function, you can just simply take the values of your existing sine function and flip it. That's right, find the reciprocal. And the domain for your cosecant function is x is such that x cannot equal to n times pi, where n is any integer. That's right, so for every integer multiple of pi, the function will be undefined. When it comes to the range for the parent function of cosecant, it'll be from negative infinity to negative 1, union 1 to positive infinity. Also, the graph of cosecant is symmetric with the origin, therefore the function is an odd function. And because it is an odd function, cosecant of negative x is equivalent to the opposite of cosecant x. All right, so good stuff to know. In fact, I'm feeling so great about this video, I'm going to give you some more information about cosecant. Another tidbit about it is that there are no x-intercepts. The parent function of cosecant has no x-intercepts. Also, its period is 2 pi. There are no minimum or maximum values, so its graph has no amplitude. There's no amplitude for cosecant. And also, since the graph is discontinuous at values of x in the form of x equals n pi, it has vertical asymptotes at these values. So every iteration of n pi, and remember we said that n was an integer, there's going to exist a vertical asymptote. Yeah, so just a little extra for your time. So let's continue on. Here we have problem number 1, where we have f of x equals cosecant of x. And this could be written in this form, or you can also see it written as f of x equals cosecant x. All right, so depending on your textbook, they may put the quantity that you're taking the cosecant of inside of parentheses, or they'll just simply have your value of x right next to it. It means the same thing. But what I want to remind you is that since this function is the reciprocal of the sine function, the first thing I'm going to want you to do is rewrite the original function and replace cosecant with sine. That's right. We're going to graph sine to help us graph cosecant. So the strategy that I use when graphing cosecant is simply to graph sine. So because of that, you may want to check out our video on graphing sine, and I'll put a link right up here. Okay? So check that video out and then come back. So let's move forward with this process, knowing that we'll be graphing sine to help us graph cosecant. All right, and here's a reminder of the information that I gave you in the sine video, and that is sine can be written in the form of y equals a times sine of bx minus c plus d, where a is the amplitude of sine, the period of sine, and cosine for that matter, is 2 pi over b, and the phase shift, where you're going to start graphing the function, will be the quotient of c and b. Your vertical shift is d, and the increment, one of the most important parts of this graphing process, is the the increments. The increments, you find that by dividing the period by 4. Yeah, let's keep it moving. So here, once again, remember we had originally f of x equals cosecant x. However, we're using sine to graph cosecant. So the first thing you should note is that your a value is 1. Yeah, a value is 1 here because you just got 1 sine x. Your period here is going to be 2 pi over b. And the coefficient on your x variable is 1. Therefore, the b value is 1. And thus, the period is 2 pi. Then for your phase shift, that's going to be c over b. We don't have a c value in this function. Therefore, the c value is 0. So therefore, 0 over 1 is just 0. So we'll be starting at 0 on our graph. Then your vertical shift here is also 0. And when it comes to finding the increments of the function, we'll go ahead and take the period, which is 2 pi, and divide that value by 4. All right. And we're also going to simplify here. So we'll end up with increments of pi over 2. Red, box it. So what we'll actually be boxing up is the fact that our period is 2 pi because that'll be the same value for our cosecant function. Remember that cosecant doesn't have an amplitude, so we're going to leave that out of the red boxing process. And we do have a phase shift of 0, so that's going to be important to keep up with. And we have a vertical shift of 0. Yeah, there we go. And then we also have increments of pi over 2. Once again, something that we want to keep in mind. All right, so let's go ahead and create our XY chart, shall we? We'll begin, of course, at 0. Remember, I said that the phase shift will always be your starting value in your XY chart. So I'll have a starting value of 0, and then I'll keep adding our increment value of pi over 2. So the next point will be at pi over 2, and then the point after that will be at pi, because pi over 2 plus pi over 2 is pi. And then adding pi over 2 to pi, you'll end up with 3 pi over 2, and finally you'll end up with 2 pi. So these are going to be our x values that we're going to be plugging into our sine function. So sine at 0 is going to be 0, and then sine at pi over 2 is positive 1. Sine of pi is 0. Sine of 3 pi over 2 is going to be negative 1. And then sine of 2 pi, once again, is 0. So these are going to be the points that we use to graph our sine function. So we're expected to eventually graph cosecant, right? So initially, I'm going to be graphing my sine function in black. All right. So our first point is going to be at 0, 0. So I got a point there. Then we have a point at pi over 2, 1. That'll give us a point right here. Thank you. And then we'll have a point at pi 0. That'll give me a point here. And then we also have a point at 3 pi negative 1. That'll give me a point right here. Thanks. And then we also have a point at 2 pi 0. All right. And so therefore, our function for sine has a graph that looks like that. Yeah. So that's our sine function. But remember, what we know is that the reciprocal of sine is cosecant. So therefore, everywhere sine is 0, there's going to be a vertical asymptote. That's right. Because if we were to place 0 in the denominator, we would end up with an undefined function. So everywhere you see sine hitting 0, you'll be ending up with a vertical asymptote. Remember that our vertical asymptotes occur at every iteration of n times pi. 0 times pi is 0, 1 times pi is pi, 2 times pi is 2 pi, and so on. So every integer multiple of pi is where you'll have a vertical asymptote for our parent function here. So I'm going to continue with a vertical asymptote at pi, and that's going to give me a vertical asymptote right here. Okay, then I'll also have a vertical asymptote at 2 pi. All right, there we go. The next thing you'll do in order to graph cosecant is simply draw parabolas in the space between the vertical asymptotes. That's it. And these parabolas are going to be bound to the space between your vertical asymptotes. And notice that they're going to have that common peak and valley with the sine function. And what you see before you in green is your graph of cosecant. That is one full period of cosecant. And if your teacher or text asks you for multiple periods, or let's say a minimum of 2 periods of the graph, then you can always continue this process to the right or continue this process to the left. For instance, knowing that I'll have a vertical asymptote at every integer multiple of pi, I can continue with a vertical asymptote right here. And knowing that my initial graph came from sine, then I'll know I'll have a value at negative pi over 2, negative 1. And I also know I have a point at negative pi 0. Okay. And then continuing on, I would end up with a point at negative 3 over pi 1. and I would have a point right there. So I could continue this graph looking just like this. All right, thereby extending our graph of cosecant. Okay, so it'd be just like that as far as what we visually have showing right here. So that's what I mean by saying that you can continue this process of extending your graph either to the left or right of your initial period that you draw. All right, and this is the graph of cosecant, ladies and gentlemen, just like that. Once again, our cosecant graph is the graph in green. We were using our graph of sine to assist us in graphing cosecant. In fact, what I'll do, I think I'll start graphing our sine function using dashed lines from now on, okay? Just to let you know that this is not the graph of cosecant. All right. There you go. So that looks better, right? So that lets you know that that dashed line is not a part of the final form of the graph. It is just a tool that we use to graph our cosecant function, which is in green, by the way. All right, let's move on. Here we have problem number 2, where we have y equals negative cosecant of pi x. Well, what we'll do in this problem is, first of all, we'll go ahead and rewrite this, all right, as y equals negative sine of pi x. Okay, remember that using the graph of sine really helps you in the process of graphing cosecant. So this is what I'm going to use to graph my cosecant function. All right, let's move on here. So rewriting our original cosecant function as a sine function, we should know that our absolute value of negative a, in other words, the absolute value of negative 1 here, is going to be 1. So we have an amplitude of 1 for the sine function that we're using. Our period is going to be 2 pi over b. Well, our b value is pi, therefore this simplifies to give you a period of 2. So our period is 2 for this function. And then our phase shift here, we don't have a c value, so that's 0. We also don't have a d value, so there's no vertical shift for this function. And our increments is going to be our period, which is 2, divided by 4. So simplifying, we'll end up with 1/2 for our increments. All right, that being the case, well, let's go ahead and begin with our x values for our xy chart, starting with our phase shift value, which is 0. So we'll start at 0 here and keep adding 1/2. So after that, you'll have 1/2. After that, you'll have 1. Then you'll have 3/2, and then you'll have 2. So these will be the x values that I use for one period of our graph. Then we'll be plugging these values into the original function. So pi times 0 is 0, and sine at 0 is 0, and the opposite of 0, you know it's 0. Okay, then let's plug in 1/2. Pi times 1/2 is pi over 2. Sine at pi over 2 is 1, and then the opposite of that is negative 1. Then plugging in 1, pi times 1 gives us pi. Sine of pi is 0, and the opposite of that is still 0. Then plugging in 3/2, we'll have pi times 3/2, which is 3 pi over 2. Sine of 3 pi over 2 is negative 1, and then the opposite of negative 1 is positive 1. Then plugging in 2, pi times 2 gives us 2 pi. Sine at 2 pi is 0, and then the opposite of that value is once again 0. So these are going to be the 5 points that I use to plot on my graph. So I have a point at 0, 0. I also have a point at 1/2 negative 1. I have a point at 1, 0. I also have a point at 3/2, 1. I end up with a point at 2, 0. And this completes one full period of our sine function, which is going to be the equivalent period of our cosecant function. And now I'll be graphing this. Remember that I want to graph this in dashed lines this time. All right, so that's going to be a lot better for the visuals. And we'll end up with vertical asymptotes at 0 as well as at 2. Remember, it's wherever sine was originally 0, that's where you're going to end up with an undefined scenario. And let's not forget the vertical asymptote that we have right here. All right, so it's because of this horizontal shrink that we have in the form of pi that squeezes this graph down. Remember that our previous graph was kind of stretched out, right? Well, because of this horizontal shrink, you're going to have a shorter widthwise graph. Okay, so that's what you end up with. But keeping in mind that since cosecant is going to be bound between the vertical asymptotes that we've graphed, and it will share that common valley and peak with sine, we'll end up with a cosecant graph that looks like this. All right, just like this, guys. All right, so that's going to complete one full period of cosecant. And once again, if you want an additional period, you should know that at every integer, we're going to have a vertical asymptote. So we'll have a vertical asymptote here at 1. We also have a vertical asymptote here at -2. And then continuing our sine function, we'll have a point at -1/2, 1. We'll have a point at -1, 0. We'll also have a point at -3/2, -1. And then, of course, it'll come back up to -2, 0. So continuing this initial dashed line that we have for our sine function, this will help me continue the graph of cosecant. Just like this, guys. All right, so there you go. So that's 2 full periods of cosecant, just like that. And remember, you can go in either direction. So I can continue to the left, I can continue to the right, and that will give me as many periods as my teacher or textbook needs for that assignment. And there you go. That's the graph of problem number 2, guys. And remember, this is the graph for y equals negative cosecant of pi x, being as though the graph in green is what we're turning in. All right, the rest of these dashed lines, this indicates vertical asymptotes as well as our sine function that we use to help graph the cosecant function. Red box it. So they'll probably want to know the period, which is going to be 2. Your phase shift is 0. Your vertical shift is going to be 0, and your increments is going to have a value of 1/2. Other values that they may want to ask you about are going to be things like the y-intercept. This graph doesn't have a y-intercept. It also does not have any x-intercepts, as I told you guys previously. And unless there's a vertical shift where they are moving this graph up or down, you won't have any x-intercepts. And that completes problem number 2. All right, I would also like to remind you guys that you can always set up a paid online tutorial today with me, Mr. Witt, and Fort Bend Tutoring. We can help you guys with online tutorials using either Skype or FaceTime. I actually prefer the FaceTime. So if you need any help with your homework, whether it be algebra, geometry, trigonometry, or calculus, go ahead and set up a paid online tutorial with Fort Bend Tutoring. And let's continue with problem number 3. Here in problem number 3, we have f of x equals cosecant of x plus pi over 2 plus 2. So my first step in this process is going to be to rewrite this initial cosecant function as a sine function. So this is going to be f of x equals sine of the quantity x plus pi over 2 plus 2. All right. And this is going to be the function that I'm going to use as a tool, as a crutch, to help me graph the cosecant function. All right, so here we have it. So with our f of x equals to sine of x plus pi over 2 plus 2, we know that the amplitude is going to be the absolute value of the a value. Well, the a value for this function is 1. So the absolute value of 1 is 1. All right, so our sine function will have an amplitude of 1. The period is going to be 2 pi divided by b. So we'll have 2 pi, and then our b value is 1. All right, notice that the coefficient in front of the x variable is 1. Therefore, the b value is 1. So this simplifies to give us a period of 2 pi. The phase shift is c over b. Now keep in mind that per our given form at the beginning of the video, that this value here is the opposite of c. Therefore, our c value will be negative pi over 2 divided by our b value, which is 1, to simplify to give us a phase shift of negative pi over 2. So the phase shift, once again, depends upon the c and the b value, and the c value is the opposite of the value that you see within the parentheses. So it's going to be a negative pi over 2 that you have divided by positive 1 in this case. That simplifies to give us negative pi over 2. And this is really important here because this is where I'm going to start my function on the graph. I always start at the phase shift. Now my vertical shift in this case is 2. Positive 2, and we get that d value at the end of the function there once it's written in that form. And finally, for the increments, it's the period divided by 4. So our period here is 2 pi divided by 4, and that will simplify to give me increments of pi over 2. Red box it. All right, so let's go ahead and box up our period, which is 2 pi. We'll box up the phase shift, aka the starting point, and we also have the vertical shift of 2, and we have our increments at pi over 2. So let's go ahead and complete the XY chart. We're going to begin with our phase shift, which is going to be at negative pi over 2. Since our increments are pi over 2, adding pi over 2 to negative pi over 2 gives you 0. Then 0 plus pi over 2 is pi over 2, and then pi over 2 plus pi over 2 gives you pi, and then pi over 2 plus pi gives you 3 pi over 2. And there we have our x values that we'll be plugging in into our sine function that will help us graph the cosecant function. So starting out with negative pi over 2, negative pi over 2 plus pi over 2 is 0, sine at 0 is 0, and so therefore your value is going to be 2. So my y value is 2, but I'm going to keep in mind that normally without any transformations, this would be where my asymptote would occur. So I'm going to make note with a VA that I have a vertical asymptote at this point of negative pi over 2, 2. Then plugging in 0, 0 plus pi over 2 gives me pi over 2, and sine at pi over 2 is 1, and then 1 plus 2 is 3. Plugging in pi over 2 here. This is a 2, not a 1, by the way. And let's go ahead and fix that 2. This 2 is just mad ugly for no reason at all. Just stupidly ugly. There we go. That's a better 2. Thank you. Thank you. So plugging in pi over 2 into our function, pi over 2 plus pi over 2 is pi, and then sine of pi is 0. 0 plus 2 is 2. So we have a point here at 2. And once again, this is going to be where a vertical asymptote would have normally occurred. It's good to write these down to keep track of them, guys, because it's easy to recognize where the vertical asymptotes would have been if these y values were 0, because it's easy to see that the reciprocal of 0 would be undefined, right? However, when you have different values due to the vertical shift here, you may want to make note of where that vertical asymptote would be if we did not have that vertical shift of 2 to begin with. So I make note of these vertical asymptotes as a personal preference to make sure I'm aware of where all of the vertical asymptotes are when I'm graphing the points. Next, we'll be plugging in pi. Pi plus pi over 2 gives us 3 pi over 2, and then taking sine of 3 pi over 2 is negative 1. Negative 1 plus 2 is 1. Then we'll be plugging in 3 pi over 2. 3 pi over 2 plus pi over 2 is 2 pi, and sine at 2 pi is 0, and 0 plus 2 is 2, with a vertical asymptote that will occur when we take the reciprocal of that. All right, well, guys, looks like we got all of our points that we need for problem number 3. So let's go ahead and plot those. Remember that the first one is going to be at negative pi over 2 and 2. So this is going to be my first point here. Then I have a point at 0, 3. Next, I'll have a point at pi over 2, 2. So that gives me a point here. Then I'll have a point at pi 1. Gives me a point here. And then we have a point at 3 pi over 2, 2. So that's going to give me a point right here. And then I'm going to be using a dashed line for my sine function here, like so. And next, I'll be graphing my vertical asymptote. So I have a vertical asymptote here. Okay, at negative pi over 2. I'll also have a vertical asymptote at pi over 2. That'll be right here. And then I also have a vertical asymptote at 3 pi over 2. Like so. And now, based on our parent function and the transformations that we put in place, I know that my cosecant function is going to be bound by the vertical asymptotes, and it's going to look like this. Okay, there we go, guys. All right, so this is going to be the graph of problem number 3, you know? And of course, you can always go to the left or right of this graph with additional periods. So you can just repeat the process, repeat those points that we found to the left or right of your existing graph that you have right now. But this is a full period of our cosecant function. So remember that the graph in green is going to be the graph of f of x equals cosecant of x plus pi over 2 plus 2. And we simply use the sine function as a tool to assist us in the graphing process. Yeah. That was problem number 3, guys. On to the next problem. In problem number 4, we have y equals 2 cosecant of 1/3 x minus 1. So what we'll do here is we'll begin by rewriting this as a sine function. So this is going to be 2 sine of 1/3 x minus 1. And this is going to be the graph that we'll use to graph our cosecant function. So we'll start out with the fact that our amplitude here for the sine function is going to be 2. Remember, that's going to be the absolute value of that a value of 2 here. Then your period is going to be 2 pi over 1/3 in this case because that's our b value. And simplifying that, 2 pi divided by 1/3 ends up being 2 pi times 3. So this is going to be 6 pi for our period. We don't have a c value, so our phase shift is going to be at 0. However, this time we do have a vertical shift, and that is going to be -1. That's that d value. Your period divided by 4 will tell you your increments. So if I take 6 pi over 4 and simplify it, that gives me 3 pi over 2 for my values. So our x values are going to be, remember we started the phase shift, it's going to be 0. Then we'll have 3 pi over 2. Next we'll have 3 pi, then we'll have 9 pi over 2, and then finally we'll be plugging in 6 pi. So these will be the 5 values of x that we plug into our sine function. Let's go ahead and red box the values that are important to us for our cosecant function, and that is we have a period of 6 pi, we have a phase shift that's 0, we also have a vertical shift of -1, and our increments are 3 pi over 2. Next, let's go ahead and get our y values for our xy chart. Plugging in 0, 1/3 times 0 is 0, sine of 0 is 0, 0 times 2 is 0, and then 0 minus 1 gives me a result of -1. And let's not forget that this is going to be where our vertical asymptote will occur. Then plugging in 3 pi over 2, 1/3 times 3 pi over 2 is pi over 2. Sine at pi over 2 is 1, 1 times 2 is 2, and then 2 minus 1 gives me a result of 1. Plugging in 3 pi, 1/3 times 3 pi is pi, and sine of pi is 0. 0 times 2 is 0, and 0 minus 1 gives me -1, and this will also have a vertical asymptote on our cosecant function. Now plugging in 9 pi over 2, 1/3 times 9 pi over 2 gives us 3 pi over 2. Sine at 3 pi over 2 is -1. -1 times 2 is -2, and -2 minus 1 gives you a result of -3. Now we'll have 6 pi to plug in for x. 1/3 times 6 pi is 2 pi, and sine at 2 pi is 0. 0 times 2 is 0, and 0 minus 1 gives you -1, and this will also have a vertical asymptote at that value of x. So plugging our points in, we'll have 0, -1, have a point here. We have a point at 3 pi over 2, 1. Then we have a point at 3 pi and -1. You'll have a point at 9 pi over 2 and -3. You'll have a point at 6 pi and -1. And using dashed lines here, you'll have your graph of sine. We know that we'll have a vertical asymptote where x equals 0. We'll have a vertical asymptote where x equals 3 pi. And we'll have a vertical asymptote where x equals to 6 pi. And now, due to the fact that we had our parent function and we know how all the transformations occur, we can go ahead and graph our cosecant function. So it's going to be trapped within the vertical asymptotes, just like that, okay? And of course, it will continue to the left and right depending on the number of periods your teacher and or assignment request. And this is the graph for y equals 2 cosecant of 1/3 x minus 1. Done and done, ladies and gentlemen. So, as a reminder, please subscribe to Fort Bend Tutoring, guys. As always, it is a pleasure helping you guys out with your assignments and preparing for upcoming tests. Please give us a like and share this video with your friends and classmates and family. We will greatly appreciate that. And if you're able, please donate, as that helps us bring you more free math tutorials from me, Mr. Witt, and Fort Bend Tutoring. Peace.
Thanks for watching. We appreciate you hanging out with Fort Bend Tutoring. Like the video, comment, and subscribe. Hit up our website, tutoringmath.net, and set up a private tutorial with me and FBT. Oh yeah, baby.